Developments in the theory of commutative rings have been driven by mainly two areas of mathematical exploration. One has been number theory and the other algebraic geometry. So in number theory, and better the solutions of Diophantine equations, and in algebraic geometry, we would like to understand the zero loci of polynomial equations. Now let's just do a little bit of number theory to get some motivation for some of the theorems we're going to learn about commutative rings. So one of the most basic theorems in number theory, very foundational, is the fundamental theorem of arithmetic. What this theorem says is that any integer, let's say n greater than 1, so at least 2, can be written as a product n equals p1 p2 pk, where p1 p2 pk are prime numbers. Moreover, this factorization is unique up to reordering of the prime factors. Okay, I'm sure you've seen this theorem before and you're familiar with it, but I'm going to just carefully go over the proof of this theorem, and we'll make certain observations about the structure of this proof, and these observations will help us generalize this theorem to other settings. Okay, so how do we prove this theorem? So let's try to prove it. So the proof goes basically by induction on it. And we'll do two parts. We'll first prove the existence of such a factorization, and then we will prove the uniqueness. So for existence, okay, so for n equals 2, obviously the result is true, n is a prime, 2 is a prime number, and so with k equals 1 you have a factorization. Okay, but suppose, assume the result to be true for all n prime less than n. Okay, so this is a strong induction hypothesis, and now we have n, and we want to show that n can be written as a product of prime numbers. So if n is a prime, then we are done. Just n is equal to p, and so it's like taking k equals 1 in the factorization. Otherwise, n has a prime factor. Call it p1. So we have n equals p1 times n prime for some n prime, and this n prime is going to be between strictly greater than 1, because we assume that n was not a prime, and it's going to be of course less than n, because p1 itself is a prime number and therefore greater than or equal to 2. And now n prime by induction hypothesis n prime has a factorization. Let's say p2 up to p, well, whatever the number is, we'll call hit k minus 1, and so n is p1, p2, pk. In fact, this proof can be turned into an algorithm for writing down the prime factorization of n. You just start with n, and then if it's a prime you stop. If it's not a prime, then you find a prime factor and then you do recursion on n prime. Okay, what about uniqueness? So for uniqueness, I'd like to point out certain things that we need to use. So one is Bezout's formula, which says that if m and n have GCD equal to D, that means if the ideal generated by m and n is the principal ideal generated by D, then there exist integers a and b such that ma plus nb is equal to D. Now, the way I've written it here, saying that the ideal generated by m and n is equal to the ideal generated by D, this is obvious, right? Because that means that D lies in the ideal generated by m and n. But the point is that this is also equivalent, as we have seen when we studied Euclidean domains, to say that the GCD of m and n is D. Okay, so just we will be using this to prove the following result, which goes back to Euclid's theorem, which says that suppose P is a prime number and P divides Mn, then either P divides M or P divides N. Okay, you can easily think of an example where this would fail if P were not a prime number, right? So if, for example, you take P equals 6, then P divides 2 into 3, but P doesn't divide 2, and P doesn't divide 3. Okay, so maybe one easy way to prove this is to use Bezout's formula. So P is a prime number, and we want to show that if P does not divide M, and P does not divide N, then P does not divide Mn. So what does it mean to show that, to say that P does not divide Mn? P does not divide Mn. Now since P is a prime number, this means that the GCD of M and P is equal to 1, which means that Ma plus PB is equal to 1 for some integers a and b. Okay, and similarly P does not divide N implies that N and P equals 1, which implies that let's say NC plus PD is equal to 1 for some C and D integers. I'm just using Bezout's formula 2 times. And now I want to show that P does not divide Mn. So what I'll try to show is that I can find integers, let's say A prime and B prime, such that Mn times A prime plus P times B prime is equal to 1. So what we'll do is we'll take this first equation here and multiply it by n. So what we get is Mna plus p and b is equal to 1. No, it's not equal to 1, is equal to n. Okay, I just took this equation here and multiplied it by n. Okay, but n is yeah, so now we have nc plus pd equal to 1, so mna plus pnb times c plus p times d is equal to 1, right? Just this is n here, this expression, and so I'm using this second thing here. And now I can expand this out and write that mn times ac plus p times nbc plus d is equal to 1. So if I call this thing a prime and I call this b prime, then I'm saying that mna prime plus pb prime is equal to 1, which implies that the GCD of mn and p is 1. So that is the proof of Euclid's theorem. And now we'll use Euclid's theorem to prove uniqueness. So suppose we have two different factorizations of an integer n. And so we have another factorization, let's say q1, ql. A priori, we don't even know that the two factorizations will have the same number of factors. So now take p1. P1 is a prime number, and p1 divides n, right? So we can write this as p1 divides q1 times q2 dot 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 qk. And now we will take this as m and this as n in Euclid's theorem. So which implies that p1 divides q1 or p1 divides q2 qk. If p1 divides q1, then what we have is, let n prime be n by p1, so that is the same as p2 pk, which is the same as q2 ql. Then by the induction hypothesis, n prime has a unique decomposition, unique factorization into prime numbers, and therefore these numbers p2 up to pk are the same as these numbers q2 up to ql up to reordering. So k equals l, and p1, p2, pk are the same as q2, ql after the ordering. And so, you know, we are done because both n is p1 times these things. Now what if p1 does not divide q1? Then that means that p1 divides q2 up to qk. So if p1 divides q2 up to qk, this is let's call this number n prime. So it's n by q1, which is q2 qk. Then n prime is p1 times n double prime, because p1 divides n prime. And so when you take the factorization of n prime into prime numbers, then P1 will be one of those primes. So P1 is equal to, P1 is one of the numbers Q2 up to Qk, Q2 up to Ql, this should be L here. P1 belongs to Q2 up to Ql. And so you can go back and reorder the factorization so that the first thing here, you can just reorder these factors Q2 up to Ql and bring the one that is equal to P1 in front. So what we have is n is equal to P1 up to Pk, and it's also P1 times Q1 prime up to, let's say Q2 prime up to Ql prime. So these are the remaining factors from here after I pulled out P1, which was one among Q2 up to Ql. And then again, by induction hypothesis, you have this number P2 up to Pk, which is equal to Q prime 2 up to Ql, and so the prime factors P2 up to Pk are the same as the prime factors Q2 prime up to Ql. Okay, so I'll let you finish off the proof from here yourself.